Okay, thank you very much. I'm talking about stable matching with complex constraints. This is also I work with Thành, Nguyen and Teytelboym. So let me start with by giving you some motivation in refugee resettlement. So in 2017, 35,000 refugees are resettled to the United States. And they are allocated to many communities around the countries. And there is evidence that the initial placements are really, really important for refugee outcomes. And for each community, they have many local level integration constraints. Okay. And you know, the settlement processes are largely ad hoc. And to improve the initial placements, some agencies, for example, HIS, use some advanced techniques like machine learning and optimization. And actually, our co-author have a paper about this. And for further improvement of the placement, we use a market design approach considering refugee preferences. And when considering preferences over the two sides of the market, this brings us to the classical many-to-one matching. And in the context of refugee resettlement, there are a set of families and a set of localities. Okay. Families have ordinal preferences over localities. And similarly, localities have ordinal preferences over families. And the most fundamental question in this problem is whether there exists a stable matching. And if it exists, can we find a stable matching? Okay. So matching is stable if it doesn't have any blocking pairs. Okay. So a blocking pairs, we have a family, a blocking pair if they prefer to match to each other than the assigned partners. And as you know, to find a stable matching, we can apply the well-known default acceptance algorithm by Gale-Shapley. However, in practice, the refugees resettlement involve much more complex constraints than the ordinal preferences. So for example, families can have sizes. So if we just consider the constraint on the size of the family, that is a knapsack constraint, because families are not divisible. And in fact, localities may have many knapsack constraints. For example, the capacity on the number of schools, the language classes, employment training, and so on and so forth. And here's an example of how multidimensional knapsack constraint look like. We have 4 families and 3 localities. And each locality, each family have some number of children, some number of adults, and some number of seniors. Okay? And each locality have capacity constraint on the number of children, number of adults, and the senior. Okay? And we can see that from this one, we cannot assign family 4 to locality 2 or 3 because of the capacity constraint on the number of children. Okay? And the only way to assign family 4 is to the locality 1. And this example shows a way of assigning all 4 families to localities. Okay. So, subject to the constraint, locality also have an optimization-based choice function. So, given a set of families, F, a locality we choose a subset of F so that it maximizes the locality linear objective function with respect to the constraints. Okay. So I have just described our model in the context of refugee resettlement. And actually, our model also fits very well in other applications like daycare allocation and college admissions. Okay. But in this talk, I will be mainly focused on refugee resettlement. So if we abstract things out from the previous example, a locality we have a linear objective function subject to a set of constraints. Okay. So with the complex constraints and optimization-based choice function, a pairwise stable matching might not exist, and even when it exists, they can be very inefficient. And one can apply the default acceptance algorithm, but again, the outcome here can be very, very inefficient. So what is the reason for that? We observe that families are complementary to localities because of the knapsack constraints. So pairwise stability and default acceptance algorithm fail to capture these complementarities. So here is an example of showing that pairwise stability is very inefficient. Okay. So we have only one locality and 102 families. And the locality has the linear objective function like this. And here, each variable x1, variable xi corresponds to family I. Okay. And it has two constraints. And you can see that matching family 1 is a pairwise stable, but the value of the objective function is only 3. While matching most of the family 3 to 102, it gives us a value of 100. So 100 is much bigger than 3, so it shows that the pairwise stable is very inefficient in this case. So to avoid the inefficiency, we consider group stability. Okay. So here is a definition of group stability. So a matching is group stable if there is no pair of locality L and a set of families F prime, which can rematch such that L can increase the linear objective functions when additionally given access to the set of families F primes. And the set of families F primes have the property that every family in F primes prefers to be matched to L. Okay? So our results so that we provide an algorithm for finding a group stable outcome that approximately satisfies all the constraints. So it means that we can find a group stable, but we need some adjustment on the constraint. And we also have the theoretical bounds of violation depends on the sparsity of the constraint matrix. And I will explain in the next slide about the sparsity of the constraint matrix. Okay? And finally, we did some simulation, and the simulation results told that the error bounds are very small in practice. Okay? So what is the sparsity of the constraint matrix? And if you look at here, we have a set of constraints for the locality. Okay? And this is the matrix constraint. And we normalize it so that the capacity in each dimension is 1. Okay? So we get a relative constraint matrix. And the sparsity of the constraint matrix is defined to be the maximum column sums of the relative constraint matrix. Okay? So let me give you an example of sparsity in refugee resettlement. So the total locality capacities on average is about 250. So you can admit 250 people. And the largest family size is 8. So if capacity for each service is roughly equal, then the sparsity is equal to 3 times 8 by 250, and which it is roughly 10%. Okay. So if we apply our theorem into this example, we can find a group stable matching for refugee resettlement if we are allowed to violate each capacity constraint at most 10%. So to find the group stable matching, we use the scarf lemma approach. And here's a formal statement of scarf lemma. Let me try to explain it briefly. There is a constraint matrix A, and each column of the constraint matrix A has a strict order over the columns with positive coefficient. And the scarf lemma says that we can find a dominating solution. Maybe it might not really make sense to you, so now let me give you some geometric representation of scarf lemma. Okay. So the polytope here is the feasible region, and it has 3 dimensions, and you can think about each dimension correspond to a good. And we have 3 dimensions here: orange, apple, and banana. And a facet correspond to a constraint. Okay, a facet in this case it is a plane here, so triangle, and associated with each faces, it have an order over the coordinates. So because we have to have 3 coordinates here, and suppose this faces have this order: orange, apple, then banana. And we can move from one vertex, let's say this one, to another vertex along the edge here. If the moving direction, if the direction we are moving here is aligned with this order of the 2 faces, this one and the other one, neighbor to the edge. So a stable solution is a vertex that you cannot move in any direction. So I hope that it makes more sense to you. Okay. So next, let me show how to use scarf lemma for stability. So to capture the pairwise stability, we can construct a constraint matrix such that each row of the matrix corresponds to a constraint, and each column corresponds to a possible blocking path. Okay. And applying scarf lemma, we can get a dominating solution, and it gives a fractional pairwise stable. Okay. Then to capture group stability, naive way is to add columns correspond to group deviation. However, this approach has some problems. The number of columns can be exponential, and the constraint matrix could be not sparse, so we cannot use the iterative routing method. So to overcome this problem, we introduce contracts with prices. So instead of each column correspond to a blocking pair, family and locality here, now each column corresponds to a contract. And a contract specifies family, locality, and a vector price, P. And the vector price needs to satisfy the condition that the total weighted sum is less than or equal to the value of the family at the locality. And in order to apply the scarf lemma, we need to specify the preference over each row. And, to make this work, we carefully choose the preference. I want to go over the details of this. And this approach has some advantages. First, the sparsity of the constraint matrix is unchanged. And secondly, the prices allow us to capture group stability in the original matrix via pairwise stability of the new matrix with the price. And when applying scarf lemma to this new matrix, we can obtain a fractional group stable matrix. And here's our informal results. First, we just can restate what I just said before. From a dominating solution, for the relative constraint, we can get a fractional group stable matching. And from a fractional group stable matching, we use the rounding method to get an integral group stable matching. But it can violate some constraint. And the violation here is at most the sparsity of the constraint matrix. Okay. So that's it all about the theoretical results. And then we do some simulations, and we apply the algorithm to the data 2017, getting from higher agency. And because of the lack of data, we draw the refugee preferences at random. And you can think about this is a worst case scenario. And also the employment likelihoods are estimated by using the paper by Chaff et al. And in this data set, the sparsity is approximately 40%. Okay? And there are 12 localities, 200 families, and 538 refugees. And we get a matching that can allocate most of the families, 194, and 590 refugees can match. And also we compute the violation. The violation actually is much smaller than the sparsity. It's 12%. And as you can see in the graph here, the violation happened only on the children constraint. For other constraints, it's not violated. And here is the literature. I just wrote a comprehensive here, but let me briefly summarize this. Most of other papers focus on pairwise stability, and our paper focused on group stability, which is a stronger notion of stability. Okay. And for future work, we would like to find more applications of our model. So right now we have seen that it can be applied in refugee resettlement, daycare allocation, and college admissions. And we want to find more applications of our model. And also we would like to consider more complex preferences for localities. For example, the nonlinear objective function instead of linear objective function. And also we would like to extend our model to more complex preferences of refugees. For example, take into account the peer effects. And finally, we would like to do more empirical studies of our algorithm. Okay, and thank you very much for the listening. I should back.
Approximately 1 plus epsilon questions. Nicole?
I was wondering, in your data set, if you drop the group stability constraints, are you able to match all the families?
I think that is a very good question. I don't know the exact answer, but I think it might be possible. But in our research here, we saw that it can allocate most of the families. So, yeah.
Cool. You do the epsilon. Is there a second question?
You can elaborate maybe a little bit on existence of group stability. So for the core, for example, there are certain well-established criteria when the core is empty and when it is not. So how would that relate to when can we find or expect to find these group stable?
I think our model says that if we can always find group stable, but if the sparsity is very high, and then maybe the outcome might not be meaningful, right? So I would say that we can always find some group stable. That answers the questions?
All right, let's thank Hai again. Thank you so much.